So where we left off was basically the discussion of this base case where we said if there's any string Si that differs from the current candidate by not just k, but k plus d, the allowed distance plus our current budget, then we can stop. And maybe this is intuitive if the string is too far away, but why does that, with the initial call of a budget of k, why is that correct? I mean, potentially there might be some other algorithm or some other way to construct a consensus where we don't walk one step, one change at a time. What's behind this base case is this lemma where it says something about the distance of any of the strings. And here it's formulated in this way. We're given some set of strings, as it could be the input to our closest string problem, and a threshold k. Now, if you can find any two strings in this set so that the Hamming distance is strictly more than 2 times k, then there cannot be any consensus string where the distance to the consensus string is at most k. And basically, you can use the lemma even by making this set here a bit smaller and kicking out one of the strings, so that here, if you have the distance between, you need it included in this statement. So that's the more convenient statement. Now, why is this true? One option would be if you have these two strings that have a distance of more than k, that means they have at least k plus 1, 2k plus 1, sorry, 2k plus 1 positions where they differ. Now, any consensus string that might try to be at distance k from both, each of these positions has some character here and a different character there. So the consensus string can pick one of those two or have a third character, but it cannot be the same for both. So it could decide to copy the first string here, but no matter what you do, if you have 2k plus 1 red positions, you're gonna pick the character from the other string in at least k plus 1 positions for one of the two strings. So say this is always A and B, just to make the notation here easier. No matter how you try to balance things out, maybe you go alternating between the two. So this is a strange 2k plus 1 because it's an even number. Let's add another one. And then here, maybe you go back to A. No matter what you do, you will pick one of the strings in the majority of the cases, which means the other string has a difference to the green consensus candidate of at least k plus 1. And this is true no matter how you choose this green string. In the other cases, it might only get worse. Another way to see this, so I mean, this would be S. These are your Si and Sj. No matter how you pick it. Another way to say the same thing is to say that the Hamming distance, that's kind of alternative proof, the Hamming distance is a metric. A metric is the minimal conditions for a function to serve as a kind of a distance. And so a metric has 3 conditions. It needs to be greater than 0 for all entries. That's obvious for the Hamming distance because it's a count. It can only count positions, so it's never going to be negative. if you put the same string in twice, then it has to be 0. That's the other condition for a metric. And that's clearly the case because we don't have any mismatches in this between the string and itself. So these are satisfied by many functions. The crucial property of a metric is the triangle inequality. Which means for any x, y, z, it has to be that the distance, if you go from x to z, that's not more than going from x to y, and then from y to z. And from my language, you can see how this is interpreted in terms of distances in, say, the Euclidean plane. If you take the distance between x and z, then taking the detour via y will never be shorter. And you cannot shortcut something by going a detour. But if these distances are not defined in the usual way, like the Euclidean metric, it could be violated. We've discussed this in the context of the traveling salesperson problem at some point. Now here you could prove that the Hamming distance is a metric, which we basically have done with this picture above here, I guess. Any kind of mismatches between the two, you can only add more mismatches by comparing with this third string. And then this property immediately follows, right? Because you take this string S, the consensus, as the detour. Okay. That's the justification for stopping at this point. Because the way we start is we start with one of our input strings, an arbitrarily chosen one, and a budget of k changes. And here we're checking for k plus initially k, so for greater than 2k. So initially that's certainly true. Then I would have an instance of the lemma directly, because then S1 would differ from Si by more than 2k. In the inductive steps, you would have to go back to S1 by undoing the changes to see that you, if this ever fails at a later stage, you would also have some Si that differs from S1 by more than 2k positions. But we might only, if that's initially true, we will immediately stop at this point, I guess. So maybe an interesting question is whether you have to do this check each time or whether it's enough to check it once at the beginning. I guess it can still happen recursively that you move away from some string and then it might cut some branches short. So it's an optimization in that case to truncate searches that are not going to succeed. Okay. We've discussed this last time a bit, but let's go back briefly. In the worst case, this early truncation never happens, say, and we have to try all the k+1 options in recursive calls, and we have to go down all the way until we reach d less than 0. So we have a depth of k, and we have a fan out of k+1. And what I claimed yesterday is that this is big O of k to the k. And in case you want a proof of that, I think that's actually a useful thing to know, but also a little trick that's just convenient to do. So if you take the ratio and compute the limit for large k, what you can do is pull out the power, right? and rewrite this. And this fraction, or this, well, I guess this term, 1 plus 1 over k to the power of k, that's something you may have seen in the context of Euler's number. And just to bring back something people from efficient algorithms will know, there's this theoretical computer science cheat sheet, a collection of many formulas. Sorry, I should switch over to, no, you see it, okay. Which has a lot of formulas. We've used some in the past from the series. We might come back to this later. There will also be one giving a representation for E. So, for example, we can use this one. The thing you should keep in mind is probably this limit. I think this is, the rest you can essentially derive from it. But the limit of 1 plus 1 over n, if x is 1, 1 plus 1 over n to the power n, that's E. That's the limit. Now, conveniently, it's also a strict inequality in the case where we use it. So for our limit, it would have been good enough to use just this. So, no, okay. I'm just going to copy the formula so we have it. Straight where we need it. So here clearly okay, I didn't copy the limits. There's a limit front. So with the limit, I didn't switch back, thanks. There's a limit in front, so the limit exactly would be E, but also any of the terms is bounded by E. So you could say strictly less than E. And of course, that's just some constant, so that's order 1. Which proves that k plus 1 to the k is big O of k to the k. And that was the claim here. The search tree size is at most this in the worst case. Now you can also think about what's the running time of the overall algorithm. So there's a few things we have to do here. We have to determine Hamming distances. We have to find these positions where a certain string differs from the current consensus candidate. And we have to modify strings, but that's relatively cheap. And with the code as given, you don't get the strongest bound, but what you can do is overall time m times L, that's the input, and then plus a factor m times k for each recursive call in the worst case. And where this comes from is from the following ideas. You do a pre-processing where you read the input and get rid of, basically keep a list of indices of the dirty columns, and you ignore the clean columns and everything that follows. The consensus can just copy the single character there. And you also reject if you have more than m times k dirty columns. That's from the previous lemma before. So for all that follows, you can effectively pretend that the strings have length at most m times k. Then you call this, this method as given above. And for some of the parts, you can do a bit smarter than just executing the code each time by definition. In particular, you can maintain the Hamming distances between the consensus string and all the strings in the input. Then looking up a Hamming distance is constant time. But whenever you do a recursive call, you have to update the distances. The good thing is going from s to s prime, we just change a single character. So also the Hamming distance is either going to change not at all or going up by 1 or down by 1. You just have to look at one position. So that's cheap to maintain. The bottleneck seems to be to determine the positions where a specific string differs from the consensus string. Now, thinking about this again now, I think you could also try to maintain the mismatch positions between the consensus string and any of the given strings, as opposed to just the Hamming distance. You could keep that in a linked list, and you could jump to the positions. You're only changing one position, so this might work to reduce the time to just m and not m times k here. But certainly what's on the slide is doable. You can maybe improve it. Certainly the dominating part will be the exponential.